So we're still in 5.2, which is about graph terminology and special graphs. And here's a really nice result that is useful sometimes. This is a theorem. We're going to call it the Handshaking Theorem. That's what our book calls it. And most books call it this. I never like the name of it, though. I think it's a bad name for a theorem, but it's called the Handshaking Theorem. So what does it say? It says if G is a graph, G is let's say an undirected graph, then the sum of the degrees of all the vertices, I'm calling the vertices V sub i's. These are all the vertices. We're going to have a finite number of vertices. We're not going to have an infinite number. And that capital V is the vertex set. So I'm summing the degree of all the vertices over the entire vertex set. So the VI's are an element of the vertex set, capital V. This is going to be equal to twice the number of edges. How do we denote the number of edges? Well, I'm going to write it like this. The cardinality of the number of edges, right? Cardinality of E. Cardinality of E, that's the number of edges. So you see those bars around E, that means the cardinality of the set, the size of the set. So the sum of all the degrees of the vertices totals up to twice the number of edges. Now that's a really easy result to prove. Let's go ahead and prove that. Nothing very hard. This was a very elementary proof. So suppose G is an undirected graph. We can't really talk about degrees of vertices in this sense if we have a directed graph. So we have to make sure it's an undirected graph. Suppose G is an undirected graph. If you decide to go to directed graphs, you have to do an in degree and an out degree. So it's a different concept for degree. So we're not paying attention to that. We're just looking at ordinary degrees of vertices. So let's think about a typical edge. Let's say here you have, let's say a Vj and a Vk, two vertices. So if there is an edge between two vertices, Vj and Vk, then the edge counts two times towards the total degree. Let's think about that carefully. Okay, so I got this blue edge right here. I'm going to make this blue. So notice that blue edge goes into Vk once, and then it goes into Vj another time. So altogether, that one single edge is going to contribute twice to the total degree. Okay, so that's one case, right, when you have two vertices that are joined together by an edge. There's another way to get an edge, and that's just from one vertex. Let's think about that case. So let's say I got just a single Vj. Single vertex. Let's make it red. So how else can we get an edge when we have just a single vertex? We can do what's called a loop, right? So the second case is if there is a loop from Vj to itself, then that single edge counts again twice 2 times. Towards the total degree, towards the total degree. Okay, let's think about this. So I got this blue edge, right? This blue edge. That's just one edge. So it's going to go into Vj one side here and the other side down below. That's counting twice towards the total degree. So in any case, however we do it, every edge is going to count twice towards the total degree, right? So it follows that, therefore, the total degree, so the sum of the degrees of all the vertices over the vertex set, capital V, is going to be twice the number of edges. That's it. All right, so not our proof. All right, so let's see, an exercise. Question. How many edges? Okay, let me delete this. This will be exercise 1. I'll do a few of these exercises. 1. How many edges? Does a graph have? With 8 vertices? Each of degree 4. Question mark. So the idea is we don't know the number of edges in the graph, but we know that there are 8 vertices and every vertex has degree 4. So here's the solution. So, what do we know? We know that the total degree, right, the sum of the degrees of all the vertices is going to be equal to twice the number of edges. Twice the number of edges. So that's 2 times the cardinality of E. Now, how many vertices do we have? We have 8, right? So I'm going to count here with my counter. I'm going to go from I equals 1, starting at 1 and going to 8. This means I'm going to have degree of V1 plus the degree of V2 plus the degree of V3, all the way up to plus degree of V8. So I'm adding up the degree of all the vertices, 1 through 8. So I'm going to use that, the fact that we have 8 vertices right here. So I'm going to count from 1 to 8. What else do we know? Well, we know that the degree of every single vertex here is 4. So I can rewrite this summation. This is the sum from I equals 1 to 8. And the degree of VI is always going to be 4, right? So I'm going to replace this with the 4. Because we know the degree of every vertex here, every vertex is of degree 4. So you have 8 vertices of degree 4. So you got the sum from 1 to 8 of 4. This is equal to twice the number of edges. If I solve this, what happens if I add up 4 plus 4 plus 4 plus 4 plus 4 plus 4? 8 times, right? Well, it's just a fancy way of saying what? 8 times 4, or 4 times 8, however you want to say that. I'm going to write this as 8 times 4. Right? We're adding up 4 plus 4 plus 4 plus 4 plus 4 plus 4 plus 4. And so we got 8 times 4 equals twice times the number of edges. Here we're going to have what? 16. No, that's, yeah. 16 is the answer. I'm getting ahead of myself. This is going to be what? 32 on the left? 32. 8 times 4 is 32 times twice the number of edges, and divide both sides by 2. You get the number of edges equals 16, right? And that's what you wanted. You wanted to find the number of edges in such a graph, right? That's what the question was. How many edges does a graph have? So 16 edges. Okay, let's see. Can we do another example? That one wasn't too hard. Let me do another example here. There's a problem here. Is it number 2? This time we're not asking about edges. Edges are pretty easy to deal with. This time we're asking about vertices, a little harder. How many vertices must a graph have if it has 20 edges and each vertex has degree 4, and each vertex has degree 4? Question mark. Okay, so this time we're looking for the number of vertices. Interesting. And here's our solution. So we don't know the number of vertices, so I'm just going to say let the size of the vertex set, so that's the cardinality of the vertex set, that's so those bars there, those bars around V mean the size of the cardinality of V, be n. So we don't know. We don't know how many vertices. So we're saying the number of vertices is n. So let there be n vertices. So using the handshake theorem, by handshake theorem, what? The sum of the degree of all the vertices is going to be twice the number of edges. Now we know how many vertices there are. No, we don't know how many vertices there are, right? The number of vertices here we're calling n. So what we're going to do for our counter we're going to start from I equals 1, and we're going to go up to n there. I equals 1 and goes to n. All right, now what else do we know? We know there are 20 edges. 20 edges. So on the right-hand side, I'm going to replace this cardinality of E with 20. It's going to give me 2 by 20 on the right-hand side, 2 times 20. And on the left-hand side, right here, we know what the degree of the VI's are, right? Every vertex has degree 4. So we can replace those with 4. So we're going to have a sum from 1 to n, and we're going to replace those with 4. Each has degree 4. So we have the sum from 1 to n, 4 equals 2 times 20. Here's the question. What's the sum from 1 to n of 4? We're adding up, what, 4 plus 4 plus 4. This should be a little lower here. Let me put this a little bit lower. 2 by 20 right here. By 20. Okay, we're adding up 4 plus 4 plus 4 plus 4 plus 4 a bunch of times, n times, right? This is going to be what? N times 4, we can say 4n, right? This is going to be 4 and adding up n a bunch of times together. On the right-hand side, we're going to have 40, right? 2 times 20 is 40, and then we're going to divide both sides by 4, and we're going to get n equals 10. So, thus, there are 10 vertices. All right, this is going to be the last situation like that, where we use handshake theorem directly. Handshake theorem, number 3. This is a little tougher. How many vertices? So again, asking vertices rather than edges. How many vertices must a graph have if it has 15 edges? If it has 15 edges, So we know the number of edges. 3 vertices of degree 4. 3 vertices of degree 4. Hey, that number 4 is showing up a lot today for degrees. And the other vertices of degree 3. And the other vertices of degree 3. Question mark. All right, so this one's a little tougher. So we don't know how many vertices there are in total. That's what we're looking for. We know there are going to be 3 of degree 4, and the other vertices are going to be of the degree 3. So I'm going to say let V1, this is going to consist of those vertices of degree 4. So I'm going to call them, let's call them U1, U2, U3, right? These are those 3 vertices of degree 4. So let V1, that set, be the vertices of degree 4. Be the vertices of degree 4. All right, and let's call V2. We'll call those what? I don't know. W1 through WK, W1, W2, WK, be the vertices of degree 3. So I'll break it up into 2 sets like that. Vertices of degree 3. So we know there are 3 vertices of degree 4. That's U1 through U3. And we'll just say there are K vertices, right? W1 through WK vertices of degree 3. All right, so now we're going to use Handshaking Theorem. Handshaking Theorem. Handshaking Theorem. By the Handshaking Theorem. The sum of all the vertices, I'm going to call them the VI's, over the whole entire vertex set V, degree of VI, is equal to twice the number of edges. Right? Now we're going to break up this this set here, right? The capital V set. Capital V set right here. Capital V set, I'll put it in black right here. That's all the vertices. You can subdivide that into V1, right? Those of degree 4, and V2, those of degree 3. So we're going to break this into 2 sums. So first we're going to have a sum that goes from 1 to 3. I equals 1 to 3, and this is degree of the UI's. We're going to call these the UI's. And then plus, that sum's going to continue. So we broke the green sum up into a blue sum and a purple sum. Then we're going to have the sum from 1 to K, right? The degree of the WK's. Or WI's, I should call them WI's. Yeah, so all the vertices, the VI's, are made up of UI's and WI's. Then on the right-hand side, we're going to have twice the number of edges. Does anybody remember what the number of edges was? I forgot. 15, right? 15 edges right here. Let's see if we can put 15 in down there. Yep. So here on the right-hand side, we know we're going to have 30. Does anybody remember what the degree of the UI's were? U1, U2, U3 all had degree 4. So we're going to put in, this is going to be the sum from 1 to 3. This was all degree 4, right? U1, U2, U3 all had degree 4. And the purple guys, the WI's, they all have degree 3. So I'm going to have here, this is going to be the sum from I equals 1 to K of 3. Now, the first dude, when you add 4 plus 4 plus 4 3 times, you're going to have what? 3 times 4. The second dude, what? You're adding up 3 plus 3 plus 3 plus 3 plus 3 k times. So you're going to have plus 3k. This is going to be equal to 30. So here I'm going to have what? 3k. And if I subtract 12 from both sides, 3 times 4 is 12, I'm going to have 30 minus 12. So 3k is going to be equal to 18, so that's going to force k to be 6. So there are 6 vertices here of degree 3. So there are 6 vertices of degree 3 and 3 vertices. We said earlier, right, that was given of degree 4. How come that 3 didn't write? I wrote 3, it didn't write. Thus, there are a total of 9 vertices. So your answer is 9. So you were given 6 of those vertices, right? And given 6 of those vertices had. You were given 3 of those vertices had degree 4, and you found that there were 6 vertices of degree 3, right? All right, I think I'm going to stop right there. Yeah, and we'll go on with a bit of this later.